Hello everyone, in this video I am going to explain applications of mesomeric effect. So mesomeric effect I have explained in previous video. In this video I am going to explain applications. Mesomeric effect explains stability of carbocation, stability of carbon ion, stability of carbon free radical, and acidic strength of organic acid, similar to inductive effect. Inductive effect can also explain all these things. Okay. Note, mesomeric effect dominate over inductive effect. When both compete with each other, then consider mesomeric effect dominating factor. Exception: for only halogen, inductive effect dominate over mesomeric effect. For remaining, mesomeric effect dominate over inductive effect. For only halogen, fluorine, chlorine, bromine, iodine, inductive effect dominate over mesomeric effect. Next, unlike inductive effect, mesomeric effect does not depends on distance. So as the distance from the substituent, as the distance from the group increases, inductive effect decreases. So after 4 carbon, inductive effect become negligible. But mesomeric effect not depends on distance. Okay. So take this one. I will explain first stability of carbocation. Right. Mesomeric effect explains stability of carbocation. Due to mesomeric effect, resonance increases. Resonance due to presence of electron releasing group, electron withdrawing groups is mesomeric effect. Resonance due to presence of some groups in a molecule is said to be mesomeric effect. So as mesomeric groups increases, resonance increases and stability also increases. Delocalization of charges increases, stability increases. So compare ABC here. If you see, this is what delocalization. It due to this one, delocalization increases like this. Here, this is only plus I group. Delocalization is not possible here. This is what plus I group. Okay. This is stabilized by resonance. Stabilized by resonance. Stabilized by resonance. So resonance like this. So positive charge comes here, double bond shift here. Here resonance is not possible because here double bond is not present, only pi electron move towards positive charge, but here double bond is not present. This group is what? Plus I group. Plus I group increases stability of carbocation. This is also stable. Here, so double bond, single bond positive, not conjugative system. This is not conjugated system. If it is not conjugated system, no resonance. No resonance means no mesomeric effect. So in that case, this is sp carbon, sp2 carbon, and this is sp3 carbon. sp2 carbon more electronegative than sp3 carbon. So this acts as minus I group. sp2 carbon withdraw bond pair electron from sp3 carbon because sp carbon more electronegative than sp2 carbon, sp2 carbon more electronegative than sp3 carbon. Thus this bond pair move towards this double bond means this positive charge electron, these electron move towards this one. Thus this act as minus I group, this is plus I group, this is stabilized by resonance. That means mesomeric effect. Which one is resonance more stable than inductive effect? Resonance nothing but mesomeric effect. So your stability order, which is more stable? Resonance stabilized cation is more stable. A more stable than here plus I minus I. Plus I increases stability of carbocation, minus I decrease stability of carbocation. So B more stable than C. Next, case 2. Here how many resonance? 3 resonance. 3 stabilized by resonance by 3 groups. stabilized by resonance from three groups. Here stabilized by resonance from two groups. So like this stabilization. Okay, shift of double bond. Here such groups are three. So double bond shift here, double bond shift here, double bond shift here, or otherwise this double bond shift here, this double bond. Such groups are three. A double bond shift here, double bond shift here, double bond shift here. Three groups. Here double bond, this double bond shift here, this double bond comes here, this double bond comes here. That's the resonance. So double bond shift here, this double bond. For this is single positive, not conjugative system. Single positive, double bond, single bond positive. This is conjugation. This pi bond in conjugation, but not this one. So like this. Stabilized by resonance from only one group. More resonance forms are possible here. Less resonance forms, very less resonance form. Thus, which one is stable? A more stable than B more stable than C, carbocation. A more stable than B more stable than C. Next, see this third question. Compare the stability of ABC. Here this is what plus I group, this is what plus I group, this is stabilized by resonance. This effect is what? Stabilized by resonance. Here this is plus I group, and here what? Stabilized by resonance. Here stabilized by resonance. So plus I group increases stability of carbocation. This is increases carbocation. This group increases stability of carbocation. This one. Total 3. Here plus I increase stability of carbocation. Resonance also increase stability of carbocation. 2 effects. Here only 1 effect. Therefore stability is A more stable than B more stable than C. A more stable than B more stable than C. So here only stabilized by resonance. Along with resonance, plus I effect is there. Along with resonance, 2 plus I effects are there. Take this one. Next, see this example. Compare stability of above 3. So carbocation. For this carbocation, only one resonating form. Here this bond shift like this, this bond shift like this. More resonance. For this, double bond always move towards positive charge, then this carbon become positive. Double bond move, then this carbon become, this double bond shift here. As resonance increases, stability of carbocation increases. So compared to A, B more stable, compared to B, C more stable. Stability order. Remember, this is stability order. Next here see double positive charge, single bond, double bond. Delocalization possible. Stabilized by resonance. Here double bond, positive charge, single bond. Stabilized by resonance. Here single bond, not conjugative. Single bond, not conjugative. Whenever double bond is not in conjugative, that become minus I group. sp2 carbon, this is sp3 carbon. From sp3 carbon, bond move like this. This is sp2 carbon, this is sp3 carbon. Bond move like this. So minus I group. Minus I group decreases stability of carbocation. Minus I group decreases stability of carbocation. So here single bond, not in conjugation. Not in conjugation means no conjugation, No conjugation mean no M effect, no mesomeric effect. No mesomeric effect means, so this is single bond, single bond. Whenever two single bonds are present, double bond act as what? Minus I group. Double bond act as minus I group. So minus I, unfavorable for cation. Only one minus I stabilized by resonance. Here, what is factor? Resonance factor. This is stabilized by resonance. Here, stabilized by resonance and minus I group, both factor. Here, no resonance, and what? No resonance and two minus I groups. Therefore, stability order is, which one is more stable? Stabilized by resonance, A more stable than stabilized by resonance, 1 minus I group. Here 2 minus I group. 1 minus I group better than 2 minus I groups. Like this. Next, here. So, stabilized by resonance from two sides. Stabilized by resonance from two sides. Stabilized by resonance two sides. Stabilized by resonance two sides. Only one side. Stabilized by resonance one side. Here, this double bond, positive charge do not move towards. This double bond cannot come here because here already double bond is there. Resonance not possible. So this is what localized charge. Remember that point, localized charges unstable. That means molecule with localized charge are unstable. Ions, species with localized charges. Localized means delocalization not possible. Delocalization means positive charge comes here. Double bond delocalization, positive charge delocalization. Delocalization leads to increase. Localization leads to decrease. This is localized, means do not move anywhere. Delocalization possible means, so by the shift of this double bond here, this positive charge comes here. This carbon become positive and this double bond move towards here. A double bond delocalized here. Double bond delocalization takes place here. Double bond do not move anywhere means double bond localized. Localized charges are unstable. Species with localized charges are unstable. Remember this point. Maybe positive charge or negative charge, that doesn't matter. They are unstable. So which one is stable among these three? Therefore, stability is which one? Stabilized by resonance from two sides more stable than stabilized by resonance from one side more stable than. Here delocalized charges are highly unstable. Okay. Next here, positive charge. So double bond, single bond, positive charge. Conjugative system. Here positive charge, single bond, double bond. Non-conjugative means this is what, which group? Therefore this is what? Minus I group. So here this is what? Conjugative means stabilized by resonance. It is this one stabilized by resonance. This is minus I effect. So minus I effect unfavorable for stability of carbocation. So definitely A more stable than B. because minus I group, this act as minus I group due to absence of conjugative system. Double bond, single bond, single bond, no conjugation. Whenever conjugation is not present, this group acts as minus I group. If conjugation is possible, this stabilizes this carbocation. If conjugation possible, mesomeric effect. If conjugation not possible, inductive effect. Okay, so that's why resonance stabilizes carbocation, but minus I group decreases stability of carbocation. A more stable than B. Okay, take this one. Next, application 2. Mesomeric effect explains stability of carbene ion. As mesomeric effect increases, stability of carbene ion increases, similar to stability of carbocation. So compare the first example 3. So here this is carbene ion, carbene ion, carbene ion. Okay. So among these three, here what resonance is possible? Stabilized by resonance. Here resonance not possible, here resonance not possible. So compare here, this is minus I group increases stability, plus I group, but here compare, this is double bonded carbon mean sp2 carbon, this is single bonded carbon mean sp3 carbon. sp2 carbon with negative charge more stable, sp2 carbon with negative charge more stable, sp2 carbon with negative charge, sp2 carbon with negative charge, sp2 carbon with negative charge more stable. Electronegativity, sp2 carbon greater than sp3 carbon. More electronegative atoms with negative charge more stable. On that criteria, which one is more stable? This is stabilized by resonance. A definitely more stable. sp2 carbon negative, sp3 carbon negative. sp2 carbon negative more stable than sp3 carbon. Here direct more resonating forms. So here more resonating form. A more stable than 2 resonating groups, and there only one resonating group. When see here, conjugation, negative charge single bond double bond, conjugation is there. Negative charge single bond double bond, conjugation is there. Negative charge single bond double bond, conjugation is there. Okay, here stabilized by resonance, yes, stabilized by resonance. Here this is stabilized by resonance, yes, stabilized by resonance. This is also stabilized by resonance, 3 cases. Here this group, CH2 group, you know, sp3 carbon. This is sp3 carbon. So CH3, alkyl groups are minus I group. This is what? Minus I group. Sorry, plus I group, electron releasing groups. Here, for this one, only stabilized by resonance, minus I effect is not there, because this is what? sp2 carbon. Only stabilized by resonance, inductive effect is not there, because charge is not adjacent. This group is not adjacent to this one, carbene ion. This group is not adjacent to carbene ion. Here resonance is adjacent, conjugative system. Here this is stabilized by resonance. Is there. This is minus I group. This is one minus I group, and this is another minus I groups. Sorry, plus I group. Alkyl groups are always plus I. CH3, CH2, CH, all are plus I groups. But plus I group decreases stability of carbene ion. Plus I group increases stability of carbocation. Plus I group mean electron donating group increases stability of carbocation. Minus I group mean electron withdrawing group. So plus I group increases stability of carbocation. Plus I group decreases stability of carbene ion. So here, as the number of plus I group increases, stability of carbene ion decreases. Here, how many groups here? Plus I group. Only one plus I group. Here no plus I effect. Here 2 plus I effect. Which one is more stable? stabilized by resonance, A more stable than here, B more stable than, B more stable because no plus I effect. Here 1 plus I, 2 plus I, compared to 2 plus I, 1 plus I is better than C. Stability like this. Next, if you comes to fourth example, here resonance is there, stabilized by resonance, Here double bond, single bond, not conjugative system, not conjugative system. Not conjugated system. Here this is what plus I group, plus I effect, and this is what conjugation. Conjugation is possible. Here conjugation not possible. Which one is more stable? A more stable than, here what? This one more stable. B more stable than C. A more stable than, this one. Stabilized by resonance plus I. Here only minus I. Here resonance is there, here resonance is not present. So A more stable than, C more stable than B. Here only resonance, okay, stabilized by resonance. Here stabilized by resonance but minus I group, plus I effect. Plus I group unfavorable for anion, but resonance is favorable. Favorable, unfavorable. Here only favorable. Resonance is favorable. Here resonance is not possible. That's why, so compare it. Here resonance possible, stabilized by resonance. Here stabilized by resonance. These two are stable. Here negative, unfavorable effect. Here no effect. This one better. A more stable than C. Between these two, B has no conjugative system. That's why B is unstable among these three. Okay. So take this one. Next, third application, mesomeric effect explains stability of carbon free radical. As mesomeric effect increases, stability of carbon free radical also increases. So compare example 1. Here resonance is there. Whenever double bond and free radical are in conjugation, homolytic bond fission takes place. Okay, here the two resonance possible, stabilized by resonance. Here also stabilized by resonance by two groups, two sides. Here no resonance because localization. Double bond for shift not possible, no resonance. That's why which one is more stable? B more stable than, because stabilized by resonance from two sides. B more stable than, A more stable than C. Here, so three resonance forms, three resonating groups, three groups resonance stabilized by resonance from three sides, two sides, stabilized by resonance from two sides, one side. So which one is more stable? Definitely this one more stable. It liberates more number of resonating structures. A more stable than, B more stable than C. Okay, take this one. Mesomeric effect explain acidic strength of organic acids. You know, for organic acid, for any other acid denoted with HA. HA gives A minus and H plus ion. So it produces H plus ion. Okay, this HA produces H plus ion, so this is what? Acid, and this is A minus is what? Conjugate base. Conjugate base, CB, conjugate base. Okay, so as note this point, as stability of acidic strength depends on acidic strength of acids depends on stability of their conjugate bases. Stability of their conjugate bases. Conjugate bases. Stability of their conjugate bases. More the stability of conjugate base, more the stability of conjugate base, more the stability of conjugate base, more is acidic strength of its acids. More is acidic strength of its acids. More is acidic strength of its acid. In that sense, as stability of conjugate base increases, acidic strength of acid increases. Since conjugate base is anion, electron withdrawing group increases stability of conjugate bases. Electron withdrawing groups, minus I groups, electron withdrawing groups means minus I groups increases stability of conjugate bases. Stability of conjugate bases. Conjugate base is anion, electron withdrawing group increases stability of anion. So electron withdrawing group increases stability of conjugate bases, which in turn increases acidic strength of acids. Acidic strength of acids. Acidic strength of acids. Finally, what we can say, minus I group increases acidic strength of acids. Minus I groups increases acidic strength of acids. Minus M groups also. Minus I groups, minus M groups, electron withdrawing groups. Electron withdrawing group increases acidic strength of acids. In inductive effect, minus I group increases acidic strength of acids. In mesomeric effect, minus M, minus I, minus M increases acidic strength of acids. Okay. So take this one, I will give some example. See examples here. First one, in first case, carboxylic acids. So acidic strength order, which one is strong acid? So to say acidic strength order, we must compare stability of their conjugate bases. Anion. Conjugate base stability increased by minus M group. Here what is minus M group? This is minus M group. Electron withdrawing from ring or not? Yes, this 5 electron comes down. This is minus M group. Here this is lone pair electron present mean plus M group. Okay. Here hydrogen no effect. Which one is more acidic, or whose conjugate base is more stable? Its conjugate base is more stable because of delocalization of negative charge. Negative charge distribution takes place, comes down. Minus M group increases stability of carbon ion conjugate base. So minus M groups increases stability of conjugate bases, and acidic strength of acids. Therefore, which one is more stable? Definitely minus M group B more acidic, B more acidic than A, neutral better than, plus M effect. Electron donating group decreases, electron donating group plus M groups. So plus M groups decreases, plus M groups decrease acidic strength of acids, acidic strength of acids. Okay, next see here, your phenol with some group, any some CH3 group. Okay, right, now compare here. Here no group, hydrogen neutral. Here methyl group, we know methyl group is what, which group? Methyl group is plus I group, plus I group. Here cyano is multiple bond conjugative system. Conjugative system means minus M group, cyano group is. Here chlorine, lone pairs, 3 lone pair. This is which group? This is plus M group, and minus I group. In inductive effect, I have given chlorine halogens in minus I groups. I have given halogens in plus M groups. So, but halogens, which is dominating between these two? This is dominating. For only halogens, mesomeric effect dominates over inductive effect. So that means take this one. Here halogens are which groups? This is which group? Halogens are minus I group. Minus M, minus I, plus I, no effect. So definitely electron withdrawing, strong electron withdrawing, mesomeric effect means minus M means withdrawing, minus I means withdrawing. Which one is strong withdrawing? Minus M withdrawing, minus I. So C more stable, strong electron withdrawing, then D, its conjugate base is more stable, or it is strong acid. Then plus I group unfavorable effect, minus I, electron withdrawing group favorable, electron releasing group unfavorable. No, neutral. So A strong acid than B. This is the effect. Next see here, halogen. For halogen, which group this is? Plus I and plus M and minus I. So here plus I, plus M is undominated, minus I dominated for halogen. Here this is what? Only plus I group. So here no group. Here plus M group, positive mesomeric group, because conjugation, lone pair, single bond, double bond. Conjugation means mesomeric effect. Here also mesomeric effect, but only for halogen. This is which group? Minus I group. Methoxy group is minus I group. But here which is dominated? Mesomeric effect dominated over inductive effect. For halogen, inductive effect dominated over mesomeric effect. Consider it as minus I group, it as plus M group. So which groups increases acidic strength of acids? Minus I groups. So this is definitely A strong acid, then no effect to plus I unfavorable, plus M unfavorable. No effect is better. C plus I plus M. Plus I better effect, so then plus M more unstable. Like this, acidic strength of acids. Take this one. Next see this example, orthonitrophenol, metanitrophenol, paranitrophenol. So nitro group is definitely what? Nitro group is definitely minus M group. Minus M group, this is also minus M group. Here also what? Minus M group, definitely minus M group. Here minus M group. Minus M group. Minus M group, and remember mesomeric effect do not depends on distance. This is close, this is far, this is very far. Thus minus M effect does not depends on mesomeric effect. Sorry, distance. Mesomeric effect does not depends on distance. Then which one is more stable? Which one is more acidic? See, compare here. Minus I group at note this point. minus I group at meta position, at minus I group at meta position not present, minus I group at meta position, mesomeric effect is not present at meta position, minus I effect at meta position is weak, minus I effect meta position is weak. Why is it weak? See here, why is it weak? Here, this one. So how do we explain? See this one. So if it's anion, conjugation is like this. This group comes here. Okay, this group comes here. This group shift here means this negative charge doesn't comes down. Whenever negative charge do not undergo delocalization, comes down. So mesomeric effect is not present, because mesomeric effect, this pi bond involved in mesomeric effect, this negative charge comes down, because whenever this become positive, immediately this bond shift here. That's why negative charge cannot comes down. That's why mesomeric effect at meta position is very weak, not considerable. Very weak, not considerable. Very weak. So which one is more stable? Minus I effect better. Here at weak, minus I effect better. Between these two, A involves hydrogen bonding. Orthonitrophenol involves orthonitrophenol involves intramolecular hydrogen bonding. Intramolecular hydrogen bonding. See this one. This is OH group. Here, intramolecular hydrogen. That hydrogen is not free to donate. Orthonitrophenol do not donate H plus ion, because that hydrogen involved in intramolecular hydrogen bonding. Therefore, order is definitely C strong acid than, and A strong acid than B. Mesomeric effect is not present at meta position. So here hydrogen, no effect, no group. Here this is which group? Methyl group is plus I group. Here nitro group definitely minus M group, but minus M group at meta position, and this is minus M group at para position. Which one is strong acid? Among these four, D strong acid, then C strong acid, then between these A strong acid, then B. Thus acidic strength varies. Okay, hope you understood well. Thank you.